All right, we're moving ahead to section 1.3. We're going to come back to 1.2 in a little bit. 1.3 is all about propositional equivalences. I've already looked at a few examples of propositional equivalences, but this section is going to go into a little more detail, and we're going to begin with some definitions of vocabulary. So these three terms, tautology, contradiction, and contingency, are types of propositions, and every proposition falls into one of these three categories. So a tautology is a proposition that is always true, regardless of the values of any variables that might be involved in it. So if you just have a true statement, that could be a tautology, right? If it's just like the constant value t is used to represent a tautology. But some propositions, some compound propositions involving variables are also tautologies. So as an example, let's look at P or not P. So regardless of the truth value of P, if P is true or false, doesn't matter, the negation of P is going to be the opposite truth value. So guaranteed, one of these two propositions in the disjunction here, one of these is going to be true. And so that would make the entire disjunction necessarily true as well, regardless of the value of P. So that's an example of a tautology. This is equivalent to T. So T represents our tautology. Now a contradiction is the opposite of that. It's a proposition which is always false. So an example of that, you can probably guess, is P and not P. Well, again, out of the two propositions P and not P, one of them is guaranteed to be false, right? Because if it's not P, then it's going to be not P. That was silly. If it isn't P, it's the negation of P, right? If it is P, well then you're done. So one of them is going to be false, and so therefore the and is guaranteed to be false. That means that this is equivalent to F. So F, the constant value F, represents a contradiction. And then a contingency is pretty much any other proposition, which is sometimes true and sometimes false depending on the values of the variables involved. So if you look at the grand world of all possible propositions, most of them are probably contingencies. All possible compound propositions involving variables, most of them are probably contingencies, and then some of them will be tautologies and some of them will be contradictions. Now let's review the idea of equivalence. We can restate the definition of equivalence now to say that A is equivalent to B if the biconditional A if and only if B is a tautology. Okay, is always true. So that's the definition of equivalence. All right, so now we've got this idea of compound propositions and we've got this idea of equivalence. And so now we're going to look at a bunch of examples. So this is a reference sheet that you will be provided with on D2L. It's a reference sheet that you'll be allowed to use during like exams and while you're working on homework. It's here for you. You don't really have to memorize these things. These are all going to be available to you. So we have three columns here actually on the first part of the reference sheet. The first column here is for propositional equivalences. This is what we're studying now. Set identities is something that we'll study in Chapter 2, and Boolean identities here are basically the same exact idea, but using notation introduced in Chapter 12. So basically these are all saying very similar things, and the context in which you look at them, whether it's logic or sets or Boolean algebra, the context in which you look at them changes slightly how you interpret these, but they're really all the same, and they have the same names. So this is essentially a set of basic propositional equivalences that we can take for granted and work with. These should be treated sort of like trig identities, right? Or the identities of algebra. In fact, some of them even have the same names. Things like the commutative law, which says propositions commute under the AND operation. P and Q is equivalent to Q and P, right? Same with OR. Actually, I was pointing to and I was saying, I was pointing to the wrong one. But anyway, and OR both commute. And OR are also both associative. This is a lot like multiplication and addition, okay? And in many ways, and acts like multiplication and OR acts like addition, except in one really big way, and that is the distributive laws. What we're used to from algebra is that multiplication distributes over addition, and that's it. But in logic, the operations and or actually distribute over one another. So there's symmetry here that you don't get in regular algebra, in like algebra of real numbers. So we have a distributive law where we can see the or operation distributing over the and operation. So P or Q and R is P or Q and P or R. That's or distributing over and. The other one here is and distributing over or. We have P and Q or R, and that gives us P and Q or P and R. So in both cases, you have this sort of distributing property. So there we go. We also have some, I want to go through some of these basic ones up here as well. Double negation we already talked about. Identity laws are pretty straightforward. If you have P and a tautology, P and true, that's equivalent to just P because it's entirely determined by the value of P. This should be thought of as similar to multiplying by 1. And in fact, T, true, is usually associated with the value 1 when you're doing things like when you're doing things in binary. And in fact, over here, you see the Boolean version of this is x times 1 equals x, right? So this is a lot like multiplying by 1. T acts like 1. It is an identity element with respect to and. False acts like 0. It's kind of like adding 0. It's an identity element with respect to or, because P or false would be equivalent to the value of P. It's determined entirely by what value P has. So there you go. So similarly, we have these domination laws, which are kind of like multiplying by 0. You know, when you multiply by 0, you get 0 no matter what, right? So similarly, if you have a proposition or true, it's going to be true no matter what. Okay, think about that. It makes sense. Proposition and false is going to be false no matter what. So those are the domination laws. It's where the value of one of the two parts is dominating the other one, and it's the other variable value becomes irrelevant. Idempotent laws are interesting. It's like P and P is the same as P by itself, okay? And P or P is the same as just P by itself. You can kind of think through those and convince yourself of the truth of those statements. So those are these. Those are probably unfamiliar, except possibly identity laws and double negative. Those are maybe less familiar. I hope commutative and associative and distributive are pretty familiar to you. And then we have these on the bottom. So now, De Morgan's law we've encountered. De Morgan's law is a way that you can deal with negating either a conjunction or a disjunction. Turns out, the way this works is when you negate a conjunction, it becomes a disjunction and both parts of it get negated. Conversely, or like rather sort of symmetrically, when you negate a disjunction, it becomes a conjunction and each of the parts gets negated. These are De Morgan's laws. This came up in the example earlier with how do you negate the statement, what was it? I'm cold and hungry. Was that the one? I am tired and hungry. Here we go. When we wanted to negate I am tired and hungry, we said I am not tired or I'm not hungry, right? All that's required to make tired and hungry false is either not tired or not hungry, or of course both. So we get or, which is an inclusive or. That is an example of the De Morgan's law, the first version of the De Morgan's law here for negating an and statement. And it works the other way as well. Now, absorption law is probably the hardest to wrap your head around, and so I'm actually going to take the absorption law and do a proof of that in a moment. But then the negation law is pretty straightforward. It's just, these are the examples that we just went over with an example of a tautology and an example of a contradiction. Those are called the negation laws. Okay, so take a look at absorption. We have, we're going to prove, which one? We're going to prove P, the first one, P or P and Q is equivalent to just P by itself. It's called absorption because essentially the Q gets absorbed and disappears. The value of P determines exactly the overall value of this compound proposition. So let's prove that. And what we're going to do is we're going to prove the absorption law using the other laws, not the other absorption law because there's two of them. I'm not going to use the other one because they're sort of related to each other, and to use one absorption law to prove the other absorption law would be kind of like circular reasoning in a way. They're called duals of one another. We don't want to do that. We want to prove absorption using other laws. So we're going to prove P or P and Q is equivalent to just P by using other laws, or identities, or equivalences, whatever you want to call them. So we're going to have, when we do a proof like this, it's nice to sort of state this is the beginning of the proof. Actually, I'm going to switch pens here. There we go. So we're going to have a column for our steps, and then we're going to have a column where we cite justifications. This is a lot like proving a trig identity, if you remember doing that. You're going to go step by step, and each step will be justified by one of the rules. And we're going to cite them by name, using the names things like idempotent, distributive, De Morgan, absorption, that kind of thing. Well, not absorption in this case. Let's start with the more complicated side of this equivalence. We're going to look at P or P and Q. Now, I challenge you to try to do this. See if you can come up with something which is going to work here. One of the things you might think to use immediately is perhaps the distributive law. Okay, so let's attempt the distributive law. The distributive law is basically the or is going to distribute over the and. So we're going to kind of do that right here. We're going to say this becomes P or P. P or P, and then the and then we'll have P or Q. P or Q. Okay, that's justified by distributive law. Okay, so what could we do next? Well, P or P, we have a rule that says that P or P is the same as just P by itself. That's the idempotent law. Okay, so P or P is the same as just P. So I'm going to say equivalent again, just P by itself. And P or Q. That is by the idempotent law. Okay. What can we do next? Well, you know, what we have, P and P or Q, that looks a lot like the other absorption law, P and P or Q. But we said we can't use the other absorption law to prove the first absorption law. They're kind of like, that would be like circular reasoning. Well, maybe we could just distribute again, right? Let's try distributing again like this. Okay. So P and P, okay. And then we're going to do P, and then, okay, then these are going to be combined with or, and then we're going to do P and Q. So P and Q, let's put parentheses. By the way, not all of my parentheses here are necessary because of the order of operations, but I like to use them just to make very clear exactly what this means. Okay, so in this case, the parentheses technically aren't necessary, but I'm going to put them in there just to make it very clear. That was by distributive law. Okay, so now we can use the idempotent law again, because idempotent works for either and or, right? They're both equivalent whenever you combine something with itself using and or. It's just itself, so that's just P or P and Q by idempotent. Okay, this doesn't seem to be working. All we've done is we've come back to where we started, right? We're going in a circle here. This is just flipping back and forth. If you take the absorption law and you use the distributive law on it, and then the idempotent to simplify, you just go back and forth between the two versions of the absorption law. Okay, this is kind of what makes them dual to one another. Well, not exactly what makes them dual to one another. We're not going to really talk about dual that much. You can read about it in the textbook if you want to. But this is sort of reflecting how they're related to each other. This is why we can't use one to prove the other. So what I want to do is actually start over. All right, so I'm going to go to a new page, and I'm going to go ahead and try this again. Let's try to prove this again. So we're going to prove P or P and Q is supposed to be equivalent to just P. And so the proof will begin, and we're going to have our steps and our justifications. Okay, so starting over, we'll start with this side, P or P and Q. This time, I want to do something completely different. So notice that the identity law says that P and true, here we go, P and true is the same as P, right? So this P right here could actually be replaced by P and true, like that. P and true, okay? And so then, if I'm replacing that by P and true, then I have that, or this part, P and Q. So I'll highlight what I've done there. The P here was replaced by P and true. That's kind of like saying X is the same as X times 1, right? It's one of these tricks where you kind of insert a times 1 into your algebra. It's very similar to that. So I'm going to justify that by the identity law right here. So we'll write identity over there. Now, the reason that was useful is because we have a format where we have P and something or P and something else. So now what we can do is actually apply the distributive law. And we're going to sort of apply it not as distributing, but more as factoring out. You may remember from algebra class that undoing the distributive law is called factoring, right? You factor out like a common factor. We're essentially going to do that here. We have P and. So we can sort of factor out that P and say P and then what's left over is going to be the true or Q. So there is applying the distributive law sort of in the maybe the reverse direction to what you're used to doing it. So I'll write distributive there. All right, so now we're getting somewhere because true or Q is interesting. If you have true or something, that's going to dominate. All right, technically we should probably, in order to apply the domination law, we should first apply the commutative law, because the domination law as written is in a different order. So Q or T, that's by commutative. I'm going to say that when you're doing this, you can skip this step. You can skip the commutative law, and you can skip the associative law, because commutative and associative are so second nature to us from like algebra of real numbers that we're all pretty comfortable with those, and I'm going to say you can skip them. So this step you don't technically need to do. The Q or true, though, is now written in the format of the domination law, and says here that anything or true is equivalent to just true. So the T is going to dominate, and the Q is going to disappear. So now we have P and true by domination. And now one last step. And true, anything and true is equivalent to itself. P and true is actually equivalent to P. So the and true, this is like the multiplying by 1, is equivalent to P by the identity. And I think that completes the proof. Of the absorption law. And when you complete a proof, sometimes you write QED at the end, which stands for Quod Erat Demonstrandum, which is Latin for that which was to be demonstrated. It's just a way of sort of saying, hey, the proof is done. It's kind of a bit of flair that mathematicians like to throw on the end of a proof. So there we go. So that demonstrates how to use the propositional equivalences from your reference sheet to prove other propositional equivalences. Here we were proving the absorption law, but in homework and assignments, I will give you other identities to prove, identities that are not on this sheet, and then you will be allowed to use any of them, including the absorption law, at your discretion. Okay, so that does it for this one.